he gets the answers. I don't know how I got the answer, but I get the answer. Yeah. Seriously, that's it. I got all the answers, and even I'm looking at the answer. See, there's a line.
That's why when it comes to reading, I'm not sure how. So
You're a brilliant mind. You're a genius. Like, he's also a genius. You're a genius. Guys, I'm a genius, guys.
You know why you got it right? Because he was in a relaxed environment. So your mind was
all the next. Yeah, but I can't remember.
What the relaxed inside
that's the problem.
We also bring the shots into the class because we become a tester. Yeah, no, but then that's
I checked in the group chat, you said module 2 is coming out, but
Yeah.
you didn't start module 2.
Yeah, no, it's not too bad. It's 10 pages this morning. We did kind of started. I was doing videos and stuff. You know the atomic radii, the sizes. Yeah, that's the main thing.
But this geometry and stuff is not, it's not going to come out, yeah?
No, it's coming out. It is naming the shape of the bond.
Okay.
I'm going to teach you that.
You got good at it. Yeah, I don't know.
So that's how I'll walk now before. I'm hoping.
I can never do that.
I used to be like that.
That's a genius, you're right, yeah.
I don't think it's
He's a magician.
Magician.
I don't know, mate. I don't know.
Mathematician.
Yeah.
Alright guys, just open up your textbooks. We're on module 2, chemical geometry. So the learning outcomes for chemical geometry is to describe the atomic and covalent radii, right? Describe the ionic radii. Remember this year, these two are just bonding, right? Your atomic radii will just be of your elements, while when we discuss covalent radii or ionic radii, it's when there's a bonded radii of a compound, right? Describe the shapes of covalent molecules. So we'll be looking at the different types of shapes, and then the last one here is describe the concept of resonance. Right, so this year is definitely coming out, right? Resonance, where you'll have to draw a resonance structure, right? In terms of atomic and covalent radii, you need to know the difference between this year. You must be able to differentiate between that there, right? And then the shapes, we'll be looking at the different types of shapes. I think there's about 6 shapes that we'll be looking at. Example like linear. Okay, so let's go to the introduction of this here, right? Once the essential differences between electrovalent and covalent compounds are appreciated, on page 33, got it? Alright, so remember we learned the different types of bonding. We went over electrovalent and covalent compounds, and now we're going to probe a little deeper, right? We're going to look at how those structures look, right? Basically, remember, all our atoms are what type of shape? Sarah? What's the shape of the Earth? What is it called? Sphere. Right? It's spherical in shape. Right? All our atoms are spherical in shape, and we looked at the atoms. We said it has a central nucleus. Around the nucleus is protons, right? And around the protons is the electron clouds. Now we're going to be looking at those electron clouds, and we're also going to be firstly looking at the radii. You all know that if we draw a circle, right, at the center, right, around the circle is called what? Our circumference,
Yeah.
right? From one end to the other end is called our diameter, right? And then half the diameter is called your radius. So what we're going to be doing is, we're going to be looking at the atomic radius, covalent radius, ionic radius. Alright, so if we're looking at basic molecules, we'll be drawing them around the spherical shape of a atom, right? It includes the electron clouds. So for example, remember we have different orbitals. We've got your s orbital and your p orbital and your d orbital. In the purpose of this year, we'll be just looking at the s and p, right? Under the p orbitals, so we got, let's say for example, we got 1s, we got 2s, and we got 2p. Under the 2p, we got 6, right? And we call this x, y, and z, right? So the p orbitals, we said it's like a dumbbell shape. You all remember the video we watched? We said the p orbitals is like a dumbbell shape, right? So if we are drawing this here, we all know that our vertical axis is our y-axis, our horizontal axis is our x-axis, and then our z-axis is like depth, it's going into the page. So our z-axis is like going into the page here, right? Now if we had to draw this here, we got our x-axis, y-axis, and z-axis. So like we said, it's a dumbbell shape here, right? So that's on the y. This x.
So that'll be a standard diagram, diagram.
Yeah. So in between this here, there are angles. There's an angle between the y and z. There's an angle between the z and the x, and there's an angle between the x and y, and there is an angle between the x and z. Sorry, x and z here.
How many angles? You got 3 angles.
Yeah, so basically you need to know that, so we got a angle between x and y. We got an angle between the x and z. Then we got an angle between y and x, which is the same thing, right? And then we got an angle between y and z, and then z and x, and then z and y. But then there's obviously this is common, right? And then so this is
and Z and Z and X.
yeah, this is common. Put 2 around that there, 2 around that there, and y and z. 4.
You have 3 there.
But anyway, basically, what we're looking at are they going to be the angles between of this here, right? I'm just showing you that this is what it will be looking like, right? And then these angles will then determine the type of shape. And which is all theory. Everything that we're going to be doing now in this module is theory. So basically, I'll give you the notes for this part here. You need to read and understand it and learn it off. Right? And then there's common things, right? So today we'll go, for chemistry, we're going to do this section. And then tomorrow I'll give you exactly the type of revision. So if you answer my revision, you can get 100% the paper. Even the level 5 question. Right? So there's nothing too hard on my side. And it's only 2 chapters here for this year. It's only this and chapter 1, right? And after this chapter, we're going to be doing acid and bases, but you're not going to get tested on that, right? So, yeah, we said that by employing spectroscopic or X-ray, we are able to see, if you zoom in to a compound, you are actually able to see where the electrons lie and the shapes that they form, right? For chlorine molecule, right? Remember, chlorine molecule it usually occurs as Cl2 in a stable form. So basically, you got a Cl. And it's a bond between 2 chlorine molecules, right? Remember that it would have been, if you look at chlorine, it's a halogen, it's in group 7. 8 minus 7, how many valence electrons? 1. So 1 valence electron each allows for a bond to occur there. We represent the bond obviously with a dash, single dash line. Single bond, right? So yeah, they say,
Sorry, Abhi, do we need to know how to draw Lewis structures?
yeah, alright. The Lewis structures was in the previous module. Alright? But I'm going to give you, like, for tomorrow's revision, I'm going to give you all the Lewis dot structures that you'll need to draw. Like something very similar, it'll be from the same group but different elements. You get what I'm saying? So I'm basically something it out. If you don't get 100% something,
And we don't put anything past us. It'll be easy.
No, you'll have to do well. It's just we're trying to get as close to the 30% as possible, right?
30% pass mark.
Yeah. So, but even if they audit you all, yeah, they might this thing.
What do you mean you want to get us close to 30%?
So remember we said that
Oh, for the
your
continuous-
T1
oh yeah, continuous.
and T2, it's 30% and then 70%, which will give you your ICAS, which will give you 100% ideally, right? And then obviously from here, we said that they take it's 40% of this here, and then 60% comes from your exams. So you add this year and this year, it will give you your promotion mark.
Just let you pass the exam.
Yeah. So either way, you still have to pass the exam. You do 40%. Sub-minimum. Yeah. So yeah, if we're looking at the chlorine molecule, right? It tells us that the bond length is equal to 1.98 A, right? This 1.98 A, right? This is a unit of measurement, all right? Which is equal to 10 to the power minus 8 centimeters. I want you to put that in a calculator. 10 times power minus 8. 10 times. Here, okay, guys. You put it as here.
So what are you putting in?
10 to the power minus 8.
10 to the power.
Is equal to power zeros. And then minus
0,
8.
0, 0, 0, 0, 0, 0.
And then you put SD here.
You got an extra 0 there.
Simba?
Well,
He's still calculating. He's
it's
trying
slightly,
to-
slightly taller than
I think he found a problem with that question. Obvious zeros.
Okay, so 1 is equal to 0, 0, 0, 0, 0.
There was master degree.
So you put 10 to the power. What's the power button? Power button minus 8. You can see it's 0.00000. 1, 2, 3, 7 zeros, 1. Right? So what does that tell you in terms of this bond? What we're looking at there, this A, the measurement, right? It tells us that this is a very, very small measurement. And that's why we use a spectroscopic or an X-ray to actually see these types of bonds, because that's how tiny these bonds are, right? And giving a covalent bond of atomic radius of 0.999 for chlorine atom, the carbon bond distance in diamond is 1.54, almost the same value that is observed in a variety of saturated hydrocarbons, giving the atomic radius of 0.77. Right? 0.77 for carbon. The interesting point is that the atomic radii are additive. Example, chlorine and carbon and chlorine bond distance observed in a variety of compounds is almost the same as that obtained by adding together the atomic radius of carbon and the atomic radius of chlorine. So basically, they're saying that if you got a carbon molecule, right, and you got a chlorine molecule, and you take the radius here, we got a radius here, and we take the radius here. Now, if we bring these two together, and the bond is created here, if you take the radius of chlorine plus the radius of carbon, it will give you the same radius of the carbon chlorine. You get it? Does everyone get it?
So you add them up.
Yeah, you
You
add
get
them
the
up.
molecule radius.
Yeah.
So
So we got the radius of carbon, we got the radius of chlorine, right? Now, these are independent radiuses in their atoms, right? Now, when we have a chlorine-carbon bond, right? When we have a chlorine-carbon bond, and we bring these two molecules together, they form a bond. It's a covalent bond that occurs between them, right? And when they have a covalent bond, this radius is equal to this radius plus that radius. So this radius is, this whole thing here, right, from here to here, is the same thing as that. Okay, everyone understands? Okay. Let's turn over and illustrating that in the next page. Turn over there. So on the next page there, we see a chlorine molecule.
Every video I'm watching the days, it's always you moving up in and
Sorry. I'm checking, watching with you. Wait.
Can you the one that's on in
Just now, the final bond, the distance between. What is this? So when they join together, the sum of
You
the
add the right there.
of the whole molecule. So
Basically,
you have
makes
chlorine
sense,
and the
That makes sense.
yeah.
Because I mean, the electrons will be
they just come together. They don't like overlapping. They just cancel
Yeah,
each other.
that's not really electrons.
You can't just overlap. So
Alright, so yeah guys, just turn over to the next page and we're looking at the chlorine. Now if you can see there that the radius of chlorine is 0.99. I want you to take it in calculators, 0.99 times it by 2, and what's your answer? 1 point
0.99
times 2.
Uh,
Right, so obviously you get it, right? There's two radiuses. If you have two molecules, it's going to be twice of that there. Then we got the radius of carbon, right? We got the carbon-carbon bond. If you got the radius of the, unfortunately it's not drawn there. There's supposed to be circles there, guys. Alright, if you can draw it with your pencil. Draw it with your pencil, guys. The carbons. I don't know why it's not there. Right, so if we take the carbon, we got 0.77 being the radius of carbon. Times that, if we have 2 carbons, we're going to times that by 2. So multiply that by 2 just to see. 0.77 times 2. Alright, so we also see that the radius between 2 carbons is 1.54. Now we've got a bond between the carbon and chlorine. Now remember what we said. What was the radius between for the chlorine? Right, and the radius for the carbon was? So we know that the radius for the carbon is 0.77. The radius for the chlorine is 0.99. So the radius for the combination of chlorine and carbon is going to be added up. So if you add 0.99 plus 0.77, you'll end up with
176.
right? So that A there, it stands, you can see the A with the circle on the top. It means atomic radii, right? It means atomic radii. But remember what we said, atomic radii is equal to what? 10 to the power? Minus 8. So if they ask you to work out this here, what's the measurement that you're going to give? You're going to say 1.76?
10 to the minus 8.
Yeah.
Centimeter.
It's, I think in meters. Let's turn off.
Centimeters.
Oh yeah, it's in centimeters, right?
10 to the minus 6.
Minus 6.
Yeah, it's in centimeters, guys. So it's times.
You said atomic radius is
Yeah.
10 to the
10 to the power minus 8.
minus 8.
Yeah.
So it will always be standard.
It's a standard set.
A standard centimeter.
Yeah, standard centimeters. Yeah.
1.76.
But if they ask you to convert your answer to meters, how are you going to do it?
Use stick method.
Meters.
Yeah, but
Times
do you
100.
now put it as 10 to minus 11 or you write down?
So it will be
How would you put
No,
it?
you just divide it by
1,000.
100
100. No.
Oh,
centimeters to
yeah.
meters.
So 10 to minus 10 then.
So you take times take 10 to the power minus 8 divided by 100. See what your answer? 10 to the power minus 8 divided by 100. It will be 10 to the power minus
Minus
6.
10.
Sorry, minus 10. Sorry.
It was,
Yeah, it's right.
building up to a calculation, yeah, I can see that.
Yeah. No, that's right. It will be because 2 units back. And that will be your answer in meters.
Sorry.
Yes.
10 to the minus.
Yeah. Why are you pressing? You're pressing the wrong one.
So,
So it says this one here. 10 power minus 8 divided by
Times 10 to the minus 8.
over here divided by 100.
So you do 10 to minus
you put
10.
down this
Yeah.
divide.
Just divide.
Yeah.
You just press divide, but you press the side button first.
So if
You want to come down from the
1.76.
exponent.
Yeah.
And when you come down from the exponent, you.
Or you press this.
Yeah.
Oh.
Yeah.
You're not going to write all this, you leave the exponent form.
Yeah, well.
Right.
Right, everyone got 1 times 10 to the power minus 10.
Yeah.
Right, obviously let's move 2 zeros, okay? Right, so yeah, let's remember that the meters, centimeters to meters. Right, so so we're looking at the bottom on page 34. The values of atomic or covalent radii for most elements are now available on the table 2.1. So if we go to table 2.1.
Yes, sir.
Oh, it's not 2.1. I don't know what it's 2.1.
Where's the one?
There's on page 30, 40, page 40.
Yeah, page 40. But they don't have all the, only got
Okay, yeah, that's I will, let me just sort that out now. Yeah. So who's not here? Sipak Manlas are not here. And Mtuko. No, he's still in the toilet.
Oh, now I know.
It's okay, cheap.
Even the soap, they took the soap and they put it in a packet and they take it forward. No, the TV, we got two TVs, and then I think the other one was, the classroom was too small. So, but now we're moving that other TV, the big TV to the other. We won't move this TV. This TV here is for the nature program. Yeah, but hey, it's hardcore, huh? You asked the lights, we need it, sir.
Hey, but you know what? Funny enough, in my area, they're stealing light pole.
Seriously?
The whole light pole is still out.
The metal.
So it's not like
Yeah.
yeah.
You know that big construction areas by Amshana, bridges,
Yeah,
bridges. Within a month, all those lights were gone.
It's
They
LEDs
were
and
cutting the light.
it's LEDs and all that.
Yeah. Must we say contractors that come there? Then what they're saying, they're not gonna be paid, they'll save money.
Yeah, no, so in our area, they came with a municipal vehicle, and then they were taking the light poles out, like exactly what you're saying, they're cutting the light poles. We thought they going to be extending the road, because they told us there's a plan for extending the road. We said, hey, at least the guys are, sorting out the road. So they cut all the light poles out and they took it out, and they took the cables and stuff. And the guys came in overalls. We were seeing these guys working every day. And then, like maybe a month later, like the guys asked, we asked our counselor, hey, what's the story? When the road extension, because it's getting dark and we don't have lights. So we're gonna get another lane or what? The guy said, no, there's no plan for that. Where did you get the idea? I said, no, there was a WhatsApp message that got sent around. And then they're like, no, they didn't. Investigated and they said, no, it was stolen.
Yeah.
So the guys came with that. It's the municipal guys who are stealing it too. They came with overalls and everything.
No, but you can buy those overalls and you can buy police uniforms.
No, but the van was a green van. It had,
They would get a color,
Stickers you can
buy an old,
Who's it?
you know when they see all the vans with tender.
Just for the
That's this radius does have any effects on the properties of the material?
what do you mean from?
I don't know, like turbines and metals and it's got
Yeah, the different.
it affects all of that.
Kind of, because the bigger the radius, the bigger, the more chance of it has of bonding and stuff. Because then the electron cloud is bigger, so it has a greater chance of creating a bond in terms of covalent bonds and so on. Then in ionic bonds it works a little different, so it affects the properties in terms of bonding. That's why this bonding works with then the next section is geometry. So the bonding comes in hand with geometry. Yeah, unfortunately, the thing.
But we have to know all these.
You need to have an idea, but I'm going to give you all tomorrow. I'll give you all
We
the
get
ones.
another sheets.
This is where the atomic radius releases down the
Yeah.
periodic table. This is showing examples of the sizes of.
Yeah.
It's giving us.
No, it's drawn to scale, and it's times 10 to the, you got the scale there, so you, yeah. This here, guys, I want you to take this down in your, on your own periodic table there, please. These arrows. You've got the increasing electronegativity already, I think.
Yeah.
Ionization energy.
Got that?
I think, yeah, Tema didn't put it there.
we
Yeah,
got-
there
we
it
got-
here.
we got all those. We got
So
all those.
increasing atomic radius, right? From this side, that side, and then going down, it's also increasing. So the biggest radius will be what?
So the one that is FR is the one.
Yeah, francium. FR.
Yeah, I said. One.
Three?
Yeah. Still.
Yeah.
Not much.
Hello.
That's not bad.
Now, replaced him with a
Right, take one. Pass it.
replacement is to Robin. They replaced the subzone.
It's amazing how you can use, use flies, huh? Sure.
Right, guys, come back. Right, so we say that values for covalent, atomic and covalent radii for most elements are available on the table. They have been evaluated by determining the bond lengths in the covalent molecules and applying the principle of additivity. Right, for metals, the internuclear distance in crystals has been shown to be approximately the same as that of a single metal-metal covalent bond, right? Where compounds containing the latter type of bond are known, the values of these bond distances in solids, however, do depend to some extent on the way that atoms are arranged in the crystal. It is essential to realize that the bond lengths in covalent compounds are dependent upon the number of covalent bonds. Right? Is this highlighted there, right? It is essential to realize that the bonds lengths in covalent compounds are dependent upon the number of covalent bonds. Example, there is a decrease in bond length along the series that follows. So the longer chains will be the carbon-carbon single bond. The carbon-carbon double bond will be smaller, and then the smallest will be the carbon-carbon triple bond. So there's a decrease there, right? As we increase the number of bonds, it's between the carbon, the size or the length decreases. As we increase the number of bonds between carbon, the length decreases. So the carbon-carbon single bond will have the longest length, while the carbon double bond will have a smaller length, and the carbon triple bond will have the smallest length.
Why is that?
It's just that the number of electrons are getting shared, right? And when they are sharing, they're bringing the bonds closer and closer. So we have, for example, so let's say, for example, here, right? We've got carbon-carbon single bond. Then we've got a carbon double bond and a carbon triple bond. Right, so around here, remember, we're satisfying the octet rule. If we satisfy the octet rule, we got 2 here, right? And we got 2, 4, 6, 8. But 2, 4, 6, 8. Around here, we're satisfying the octet rule. We got 2, 4 already. So around this carbon, we're going to have 6 and we have 8. Around this carbon, we are going to have 6 and 8. Now we've got 2, 4, 6, right?
1, 1.
So it's going to be
1, 1.
right? You'll get it, right? So in terms of
I
this,
think, I think Abhi, we need to learn how to draw Lewis structures. I think that's where.
yeah. Okay, now I'll do that. So, but anyway, but this get the theory behind this, right?
Okay.
So this is called an octet rule, right? So where we have 8 electrons around an element, right? So what they're saying is here, the thing what I told you to highlight, it might come out not in my test but in the exam, is that as we increase the number of bonds, the structure or the length will become smaller. As we increase the number of carbon bonds, the length will become smaller. So over here we have a single bond. Right, what can you see here? The electrons around here, it's 2, 4, 6 electrons around this carbon. The 6 electrons. Remember, when electrons are not bonded to something else, they are floating around. They are floating around, which makes the length of the carbon bigger. Remember, they're in a cloud and they're floating around here somewhere, like this here. Like these 2, 4 will be like here, here, here. So we're looking at the length from here to here. It's a greater length. When you got here, they're only floating around. There's only 4 electrons floating around. So the electron clouds are smaller. And then over here, you got only 2 floating around. So the electron clouds are even smaller. So when the electron clouds are smaller, what happens to the atomic radius? It becomes smaller. So therefore, as we increase the number of bonds, the radius or the lengths become smaller. Does everybody understand? Anyone lost?
But then that means atomic number of those things are reducing,
Atomic number.
What's atomic number?
Radius.
Atomic
Radius, yeah.
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 It's actually reducing them.
Yes.
So that means the normal number would
So the in terms of the length, right, of these bonds, the carbon-carbon straight chain will always have the longest length, while the carbon-carbon double bond will always have a shorter length, and then as you increase the number of bonds, then it will become more and more compact. Because you can imagine like it's holding on tightly to something, right? When it's, they say you can have electrons floating around, or like a magnet is pulling it to the center. The more magnets you have pulling it to center, the more electrons are going to get attracted to that magnet. You get what I'm saying?
So that means can we still calculate it the same way we were doing like with the carbon and chlorine?
In terms of the bond length,
Yeah, you wouldn't be able to calculate it the same. It wouldn't be able
yeah.
to
So
calculate it.
basically, it'll be a carbon, and remember, it's a different bond. Yeah, the length will be different. Yeah, will be different. This carbon is a single thing where we can do the length of that there. While the carbon triple bond is coming more interlocked. Yeah, it's overlapping more. You understand now?
Yeah, no, I'm adding.
All right. All right. So, yeah. Okay. You all highlighted that there. We said that it's essential to realize that the bond lengths in covalent compounds are dependent upon the number of covalent links, two atoms together. Example, there's a decrease in the bond length along the series carbon-carbon, carbon double bond, carbon-carbon triple bond. And the compounds containing single covalent bonds must be used to compute the atomic radii. Right? A crystal of sodium chloride, right? You'll know that sodium chloride is NaCl, consists of a symmetrical arrangement of sodium and chloride ions. Right? Each sodium ion is being surrounded by 6 chloride ions, right? And vice versa. The inter-ionic distance, right? So this is where we're looking at ionic radii. Because remember, the bond between a NaCl is an ionic or electrovalent bond, right? So the inter-ionic distance, right, from the center of one ion to the center of the nearest neighbor of opposite charges was found to be 2.81 A for sodium chloride. Right? For sodium chloride, the distance between one center to the other center is 2.81. Right? Other alkali metal halides adopt the sodium chloride structure, but with different inter-ionic distances. So just like we have sodium chloride, right? Then we have potassium chloride, which is the same. What type of bond between potassium and chlorine? What type of bond? Ionic. Okay, look in the periodic table where potassium is. First, and then where's chlorine is in group 7. So group 1 and group 7. We can see the extreme left, extreme right. Remember, which is the metal? And the non-metal? Chlorine, right? Metal, non-metal, ionic bond. Right, the same thing here. We see that what they're trying to illustrate is, although potassium and sodium, they're in the same what? Same group, but if we look at the atomic radii, for the NaCl, we have 2.81, but for potassium chloride, we have 3.14. So remember what you drew on your periodic table. We said as we move down the groups, it is going to increase also in atomic radius. So in other words, potassium has a larger radius than sodium.
Okay, right. So you have to look at the.
Yeah.
I ask you which one has the between the two ionic compounds,
Yeah.
KCl and NaCl. You have to look at the sodium and the
This is
potassium.
exactly what I'm going to ask in the test. Exactly. I'm going to give you two compounds. You're going to compare the compounds, and you need to explain to me why the other compound has a larger radius.
Yes.
Right? This is exactly this question here. It's out, right? So chlorine and fluorine, right? Sorry, potassium and fluorine. So we're now looking at the next thing, next halogen. If you look at the halogen list in group 7, we initially looked at chlorine. Now we're moving down there and we're looking at fluorine. Well, actually fluorine is above chlorine. Fluorine is the first halogen there. Right, so when we're looking at fluorine, the atomic radii that's between potassium and fluorine, it's 2.66, right? And then we look at the difference between sodium and fluorine is 2.31, right? And we see that the difference between those two is 0.35, and the difference between the other one is 0.33, right? And then we minus the differences there. Basically, they're trying to show you the distance between chlorine and fluorine, right? If you're keeping your metal constant and you're looking at chlorine and fluorine, you'll see that the distance is 0.48.
So now, with this type of a question, will you be giving us that each
I'll be giving you all the atomic radii.
Okay.
Sorry,
Yeah.
just to recap, right? So we're doing covalent bonds, right?
Yeah.
If the two particles, atoms are coming together,
Yeah.
calculate the atomic radius, we add them up, right? That's
Right.
for covalent bonds.
Yeah.
For ionic bonds, right, we take the size of the radius,
Yeah.
we divide,
Not divide.
sorry, we subtract difference.
Yeah, no, you're
So
getting
it's,
confused
Okay,
here.
okay,
Yeah.
okay.
So what we're trying to do is, we're comparing the bond between potassium and chlorine initially, and then we're comparing the bond between potassium and fluorine.
So this
What the aim of this is trying to prove is that chlorine, right, has a bigger atomic radius than fluorine.
Yeah.
And the amount that it's bigger is 0.48. Then we compare chlorine and fluorine when we have it combined with sodium. And then when you look at the bond difference, right, chlorine is 0.5 bigger. Yeah. So basically what they're trying to tell you is that as we move down the periodic table, the atomic radius is
Getting bigger.
yeah, and then we look at the comparing potassium and sodium on the horizontal way there.
Okay, I get that. I thought it was
Right.
like some sort of calculation. that
Yeah.
you know.
No, so
But
basically it's understanding.
Yeah.
All there's no calculations there. You're working too much maths and science. You're looking at calculation. It's only about theory here, right? Just understanding what's going on, right? The calculation is basic, it's just adding or minusing to understand what's going on. Right, so what they say is that there's almost, you can see the difference. The difference is 0.48 and 0.50. And then the differences in the other, when comparing what you call this, potassium and sodium, the difference was 0.33 and 0.35. They're saying that it is almost constant differences are explained if we assume that each ion acts as a sphere of constant radius. The measured inter-ionic distance being represented by two spheres that are just in contact. In order to determine the actual radius of an ion, we must obviously have more information. Right? Several methods of approach have been used, the earliest and most readily understood being introduced by Lande in 1920. Right? Lande's method basically this year they're going into some theory, right? This Lande's method, and they're talking about how they came about working out atomic radii for ionic bonds, right? So we move down there, and we see that once ionic radiuses, we're on the second last paragraph on the page 35, second last paragraph. Once the ionic radiuses of one ion has been fixed, it becomes possible to determine the absolute values for the other ions. The values used to construct the table 2.1 together with the values of the atomic radii are due to Pauling, who used more refined but more complex methods. So basically what they were trying to show you here, is that they're doing something and comparing sizes in order to work out constant, and then they worked out how the atomic radii works on the periodic table. Right? So that's what your understanding should be here. Turn over. And then it is showing us the calculations used by Landis, his method. He used trigonometry here, right? Remember, you got a 45 and 45 degrees, right? And then this is what type of triangle? What type of triangle? Right angle triangle, right? Remember, all angles of a triangle add up to 180. So you got 45 and 45 is 90. The remaining angle will be a 90-degree angle. So you have your hypotenuse there, right? Which is your longest length on the triangle. It's going to be 2r. Can you all see that? R and R. R plus R, 2r. And then you got your, this thing. Your opposite is going to be a root 2 of r. And then you can work out your adjacent, right? The remaining angle by using your trig ratios. You remember Soka Chowa, right? You can just work it out there. So basically, this guy landed. He took trigonometry and he worked out the radii, right? After correcting for screening of nucleus by neutrons, he was able to compute the values for effective nuclear charges of potassium and chlorine ions. He now assumed the inter-ionic distance could be divided into the inverse ratio of these computed nuclear charges, and so arrived at values for ionic radii of both potassium and chlorine, from which other values of ionic radii could be derived. And then they say, yeah, this is the highlight, this is the point that you need to take away from here. So highlight it there. Ionic radii, like atomic radii, are subjected to slight variation, and their values depend to some extent on the manner in which the ions are packed together in the crystal. And then in 2.3, figure 2.3, we look at the atomic and ionic radii table, right? Where they show us the difference, right, in the atomic and ionic radii. And remember, your ionic one is the one with the charges. The ionic radii are the one with the charges, right? While the atomic radii is just the element on its own. Can you all see that? You can see the Li plus, and then we can see Li there. You can see Be and Be2 plus. What do you see in terms of ionic radii versus your atomic radii? Which one is bigger? It's the atomic radii. Why? Chemba, tell us why. You know this one. You asked me the question 2 weeks ago, remember? Explain to the class, why is ionic radii smaller than atomic radii?
And depending on your stages, one has to swing to another.
Remember, if it's a positive charge, just say for example, we've got lithium, and then we got lithium radii, the normal atomic radii, and then we got the lithium plus ionic radii. Now, as we can see there, that the lithium plus ionic radii is smaller than just the lithium element on its own. Now, explain to them why is that.
Because the lithium plus has lost an electron.
Right, that's the thing. Whenever you have a positive charge on an element, means it has lost an electron. Now, when you look at this sp orbitals, when you lose an electron, right, what happens? It can jump from just having an s and p orbital to not having a p orbital at all. Right? And when you're looking at the orbitals, remember it's circles and it's size. So we decrease, take an electron out from the electron cloud on the outermost cloud, what's going to happen now?
Smaller.
It's going to become smaller. So therefore your ionic radii will always be smaller. Right? But
not always.
not always. So
because if you got an
explain.
atom, you got an atom,
we have a proton.
it's got an ion that's a minus.
Yes.
It's gonna be bigger because it's gaining electron.
Right. That's what we're saying here. So if we have -2, we're looking at the negative. We're looking at the negative ions. Remember what's your negative ions called?
Electron.
No.
Anions.
Anions. Right. So we're looking at the cations. Cations will always be smaller. But if we're looking at our anions, these anions have extra electrons. Remember what happens when we have extra electrons? The clouds are going to get bigger. Alright? Everyone understands? Anyone lost? And let's move on there, right? So they say that several distinctive features are apparent in figure 2.3. So in figure 2.3, we've got all these elements. We've got them in the atomic form and the ionic form, right? Now we look closer and study what we were discussing, right? The atomic radii are very much smaller than the anionic radii. What's the anionic radii? The ones that are negatively charged. Just write that down on top so you don't forget. Anionic means negatively charged. So we're comparing the atomic radii to that of the anionic radii. Now let's look at the first one there. We're comparing chlorine. The normal atomic radii for chlorine is 0.99. But now for Cl minus, the atomic radii is 1.81. And then we look at sodium, right? Now this is, sodium is what? Remember, sodium is a metal.
Yeah.
So in terms of its ions, it's actually a cation because this is positive, right? So our normal atomic radii for sodium is 1.57, right? While our cation or ionic radii is 0.95. Right? What does it tell you? That when it is positively charged, the radii becomes smaller. Right? Atomic and ionic radii increase down a particular period group since it works the same though, guys. Atomic and ionic radii increase as we go down. They increase in size as we go down. And which other way do they increase? Going down and from? Yes, right? So atomic and ionic radii increase down a particular period group since the number of electronic shells increases. And the shells, remember as we said, as we move down the period, the number of shells increase. That means we go from S to P to D, right? And the increase in the nuclear charge is insufficient to counteract this expansion, right? And then we're looking at other molecules there. We're looking at fluorine, we've got 0.72, and then we're looking at the fluorine anion, which is minus 1.36. Looking at the chlorine, 0.99, and the chlorine anion is 1.81. Looking at bromine, 1.14, and bromine ion 1.95, right? And then same for iodine, which is 1.33, and then bromine anion is 2.16, right? Atomic radii decreases across a particular period, right? Since additional electrons enter the same shell, an increase in nuclear charge exerts a contracting effect. For example, for lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. The radii of isoelectronic positive ions with the same number of J of electrons decreases with increased charge. There's only a small small decrease, small I decrease in the radii of isoelectronic negative ions, decreasing in negative charge. So if we look at something like lithium plus and beryllium 2 plus, I want you to find that in the periodic table for me. Find Li,
Number 3.
right?
1.
Number
3.
1 and 3, 2 and 3. Li and Be, they're next to each other, right?
Yeah.
So if we're looking at, we know that these are metals, right? And they are positively charged. So if we're looking at them in terms of the cation form, lithium positive 2 plus and beryllium 2 plus. What do we see there? Which one has a bigger? Yeah. Yeah, so what does it tell us? So we remember we were saying that we're moving this way and we are increases in size. So obviously lithium is more on the left hand side, so it will have a bigger atomic radius, ionic radius than beryllium. While the opposite is true, I want you to look at sulfur and chlorine. Find sulfur for me. Right, so they're also next to each other. Right, but we see that sulfur 2 minus, right, has a larger radii than our chlorine. Right, what does it tell us? Once again, as we're moving more, where's sulfur to chlorine? It's more to the
left.
right. If we're to compare sulfur and argon, AR, right, you'll get it now, guys. Okay, so let's move on. Transition metals. So where's your transition metals? You look at your transition metals.
From 2
Center.
1 to
Yeah. So we look at from SC to ZN.
zinc.
SC to, right. So yeah, transition metals show variation, show little variation in atomic size. They say that transition metals show little variation. So I want you to go to this table here. You see this one here. Let's look at the atomic radii of the transition metals. What can you notice about these circles here, or the spheres?
Almost the same.
It's almost the same size, right? There is a slight difference, but they're relatively the same size, right? So transition metals show a little variation in atomic size. Along a given transition series, there's small decreases in size of the atom. And they say at least for the first 5 or 6 members, as additionally electrons enter the penultimate shell and the D level fills. So basically they're saying it enters, you get different types of shells, and we come up to the D, which is your largest shells that we'll find, right? They say, note, since an electrovalent bond, ionic bond, they say, since an ionic bond is non-directional, there's no direction in an ionic bond, right? In which, like a polar bond, we know there's an attraction from one pole to the other pole, right? While in an electrovalent bond, it's non-directional, and an ionic solid will consist of a symmetrical array of positive and negative ions.
Sorry, just
Yeah.
answer the question.
Yeah.
Ionic bond, you got a positive and negative charge,
Right.
coming
Right.
together. Won't there be attraction force coming together? So it would be directional.
Yeah, but it needs if it's close to each other, then we just consider it an attraction force between a metal and non-metal, right? But if it's on one end of the pole and another end, then we have a directional bond on it, right? But that is the dipole forces. Remember the pole? Yeah. Right. Yeah. So as many positive ions surround the negative ion and vice versa as a consistent, right? Maintaining electrically neutrality, ensuring the maximum lattice energy, right? Okay, let's consider a hypothetical case of an ionic solid. We have ionic solid, right? So we're going to have an anion, which we're going to call it A plus. Sorry, cation, we're going to call it A plus. And we have an anion, we're going to call it B minus, right? Which both ions are identical in size, right? So it is easy to show, right, that each A plus ion can be surrounded by 6 B minus ions. So if you look at the 2.4, you can see the A plus on top. On the top, it's in the center, and around that there's 6. So I want you to highlight the 6 around it. And you maybe highlight the A plus a different color. Yeah, that's a nice highlighter. Put all the colors.
No, sorry.
Stealing from the light here in the whole. Right. Yeah, they say, consider the hypothetical case. We've got A plus and B minus, in which both the ions are identical in size. It is easy to show that the A plus ions can be surrounded by 6 B minus ions in the same plane, so that each B ion touches the A plus ion. Right? It is possible to place another 3 B ions above the first layer. Right? So we've got above the first layer, we can put 3 B plus, B minus, so that these 6 ions are just in contact with A plus ion. There are therefore 12 B minus ions in contact with each A plus ion, and coordination number of the A plus ion is said to be 12. In order to preserve electrical neutrality, that means it doesn't have an overall charge. When you say electrical neutrality, it means it doesn't have an overall charge. It's not a negative or positive charge, right? The coordination number of B minus ion must also be 12, right? If an attempt is made to pack more than 12 B minus ions around the A plus ion, it is found that the ions opposite charge no longer touch each other. Thus, there is a lowering of the forces of attraction between them because of the increased separation, and results in a lowering of the lattice energy, right? Because remember what we said, in the situation, we're trying to ensure maximum lattice energy, and we're also trying to maintain electrical neutrality. Remember we said that in points A and B, right? As a general principle, it can be stated that the ions of opposite charge, which are the nearest neighbors, tend to touch each other, and so doing a maximum force of attraction between them is achieved. In practice, ions opposite charge are not of equal sizes, right? Cations tend to be smaller than anions as a general rule, and thus coordination numbers tend to be less than 12. Right, so then they say consider sodium chloride, NaCl structure, where each ion has a coordination number of 6. That is, each ion is surrounded by 4 coplanar ones of opposite charge above the plane and below. By considering the situation depicted in 2.4, where the size of an anion is gradually increased, it is possible to determine the critical ratio or radius of cation over radius of anion. Just remember that critical ratio, let's write this down. This here, right? I want you to write this down. Critical ratio is equal to the radius of the cation over the radius of the anion. or we can either call it as the radius ratio, right, as it is called. When a lower coordination number, a number must be adopted. And then it's showing us that in terms of it, we're looking at the positive in the center, and we got 4 around it, and we're working out the angle to be 45 degrees, right? And then whether we increase or not, the ratio is still the same. Can you see that? The ratio of the sizes of the anions to cations is still the same in A, B, and C. Can you see that?
Yeah.
Right? The limiting condition for this here is 6:6, right? The critical situation is shown in 2.5b, where an anion is just a contact with other anions and cations, right? By simple geometry, we can see that AB is equal to CB cos 45. Remember this here, guys? And then we look at this here. Right?
We have your arm moment, is it?
Over. Hypotenuse. Right?
It's up. Oh, it's one of the relations there.
So AB is equal to CB cos 45. Let's look at this here, right? We're using our trig ratios. Right, we got, remember SOHCAHTOA? We got the adjacent and hypotenuse that we're looking at, right? So our adjacent is AB and our hypotenuse is going to be CB, right? Can you all see that?
Yeah.
And then this by working out, so we want to work out AB here. We just move this around using maths. We take the CB, it's division here. When we take it to the other side of the equation, it becomes multiplication. So it becomes CB cos 45. Therefore, AB is equal to CB cos 45. Right? I'm sure you would have done this in science, right?
Yeah.
Yeah, as well.
Even though we're doing in chemistry.
In science, in chemistry.
Yeah, but
Check here, Abby, you got X, Y, Z in chemistry there, you got SOHCAHTOA, angles.
It's looking hectic, but it's not that hectic. It's not that hectic. It's looking, just looking at it like this here, it looks hectic, but it's not. Right? But yeah, so basically, we are working on the simple geometry, so we can work out the center. Remember, we're working out AB, which is the distance from the center of the cation, right, to that of the center of any of the anions. AB, right, is a distance from the center of the cation to the center of any of the anions. Can you all see that?
No.
No.
It's a V.
Oh, sorry, AB is the radius
Yeah.
of the anion.
Now we understand.
Yeah, AB is the radius of the anion. Alright, and then they're telling you over there the radius of an anion is equal to the sum of the radii of the cation all over the root of 2. But you'll understand it when I put it down like this, right?
They will ask us to.
No, I'm not asking you.
Damn.
In exams, it doesn't even come out. And then we're looking at, remember what we're trying to work out? We're trying to work out the critical ratio, which is the radius of the cation over the radius of the anion. We worked out the radius of the anion to be CB cos 45. The radius of the anion is CB cos 45. But if we look at it in terms of putting into working on the critical ratio, if we turn over, radius of the cation over the radius of the anion will be root 2 minus 1, which is 0.414, right? If this is the radius ratio is less than 0.414, a binary ionic compound must adopt a structure with a coordination number less than 6. On the other hand, a coordination number greater than 6 can be achieved if the radius ratio exceeds 0.732. Example, calcium chloride structure, which has a coordination number of 8. Table 2.1 lists some compounds having the sodium chloride and calcium chloride structures. The radius ratio or criteria being deduced by simple geometrical arguments. Yeah, so in terms of this here, I'm not going to test you on this here, and it usually doesn't come on the exams. So I want you to, obviously we need at least reading knowledge on all of this, right? But it's not actually, we're not actually testing you on this here, right? So yeah, I think I'm listening to you, okay, let's get confused here.
Yeah, let's keep it.
I don't know, let's keep it, let me just read over it. In case something happens and it does come out, then you'll say, hey, remember that, sir? You said, read over it. Right, so type of structure, we're looking at the calcium chloride, and then example we got CsCl minus, right? Cs plus Br minus and Cs plus I minus, right? So basically we're looking at calcium with different halogens there, and we look at the halogen of chlorine, bromine, and iodine. And then we're looking at sodium with different halogens. We're looking at sodium and chlorine, sodium and bromine. And then we're looking at potassium and chlorine and potassium and bromine. So all of these are ionic bonds, right? And we're looking at the radius ratio, right? The radius ratio, remember what the radius ratio is, the same thing as a critical ratio. This is the same thing as a radius ratio. Remember your radius ratio and your critical ratio is the same thing.